Okay, so the straight source is creating straight waves that are propagating from your right to left. Okay, you can see bright and dark fringes, or not fringe, I shouldn't say fringes, bright and dark lines on the floor to represent those waves. Turn it off for a second. And those are occurring because of the curvature of the water. That curvature is acting as a lens, so to speak. Would the crest of the wave correspond to a bright line or a dark line?
A dark line?
Why?
Because it would diffract the light sooner, so it would get
Refract the light.
sooner, so it would get sent out of the area, whereas a trough would keep it in.
Afraid not. Okay.
The shape of the top of the wave. I had the word.
Convex. Is that the word?
Yeah, but I was going to say like what the light actually does.
Yeah. So
divergence.
the
That's what it is.
well, actually, the other way around. The upper curved surface of the trough acts like a convex lens. From Grey 10 optics, a convex lens generally converges the light. So the bright spots are crests, and the troughs are a concave lens which diverges the light, okay, and spreads it out and produces the dark lines. So the dark lines are troughs, okay? All right, so back to waves. And if I decrease the frequency of the wave generator, that increases the wavelength, the distance between the waves. They're still moving across the floor at the same speed because that's determined by the depth of the water. All right, so what I'm going to do now is put in a barrier. And send the waves towards it. And they reflect and head back the other way. Now, if I leave it on for a second, you probably glimpsed it in there as well. What's happening right close to the barrier? Where the incoming wave is passing through the outgoing reflected wave, and they're traveling in opposite directions, and they have the same amplitude and wavelength, and they're all over it. Yes? What's that? It's a standing wave in 2 dimensions, right? 2 waves of equal amplitude and wavelength traveling in opposite directions through the same medium. So that's a 2-dimensional standing wave. What you'll see, I'll show it again, is right close to the barrier, those bright things are just flickering on and off, but they're not traveling anywhere. Right? That's a standing wave. All right, so now I'm going to have the waves hit this barrier at an angle. And off they go. Now, it's kind of misleading when they're overlapping and interfering with each other, because what I want to do is look at the direction those waves are traveling. And initially, I think I've got it about right. They're traveling in that direction. The wave fronts are lined up with that other segment, more or less. And after they bounce, you got to wait till the interference is gone. Look at that last bit right there. They're heading off in about that direction. Because while the interference is happening, my eye tends to think it's going that way. But there it is there. Right there. All right. So looking at that, if I find another one of these, here it is. There's basically the laws, or one of the laws of reflection right there, more or less angle of incidence equal angle of reflection. Okay? All right, now this next one didn't work very well the other period because I I didn't have the right weights with me because Mr. Hoya was using them to test bridges, but I need weights to hold this thing in place. But I'm gonna ask Liam to step forward or move his chair forward a bit. And I'm just gonna hold on to this so it doesn't move. And with another hand, if you could very carefully, no, here, push that in just a smidgen. In that way, okay. So I'm trying to get something resembling a parabolic shape here, okay? With our fingers out of the way. And where do you see those reflected waves going after they hit that parabolic barrier? Right by the end of my toe there, there's a focal point where those reflected straight waves are coming into that spot. And if you look at them, and they're not really showing up terribly well, but after they go through that spot, they should continue, and really not showing it at all because we're moving this thing too much. I'm moving it too much. Holy cow, it's all me. There we go, nope. We should see something resembling circular waves heading out from that spot. Kind of there. But they've lost a lot of their energy by now, so they're not showing up all that well. But trust me, they're there. Okay. All right, next thing. I'm going to put this barrier in, but only with one side. What am I about to demonstrate? Diffraction. These waves are going to pass by this barrier, and on my side of that line is a shadow area. It's behind the barrier, and there shouldn't be any waves, but there definitely are. Not much, but they're there. But if I reduce the frequency, increase the wavelength, they definitely spread out a bit more. Okay? So more diffraction at longer wavelengths. And to make it even more noticeable, make it not just a one-sided barrier, but an opening in a barrier. We should get some nice diffraction here. Okay. And again, if I decrease or increase the wavelength, they spread even more. There's a little bit less amplitude, but that's very noticeable spreading of those waves, almost like a point source. All right? Which is very relevant to Young's double slit experiment. Right. Now, I'm going to put some glass in the tank. A whole bunch of pieces of glass stacked on each other. What do you think I'm about to try and demonstrate here? Maybe semi-successfully, because it's tricky.
Diffraction.
Right. So changing the conditions in the medium, the depth of the water, should have some, or does have some small impact on the speed of the waves, and we should see that difference on the floor. It's very slight. I have more glass. I have one more piece of glass.
You can kind of see them falling behind the waves next to them.
But yeah, if you look at the transition between shallow and deep, right, there's a little bit of an angle there, indicating that these ones are a little bit further down the floor than these ones. That slight angle to the transition. I'm going to put another piece of glass in and maybe it'll become a little more pronounced. But I'm not sure I have enough water. Go water, go. Let it all settle down. And there's a definite change there. Obvious difference in speed. Okay. So next, I'm gonna put the put that boundary at an angle,
Now it's fresh.
and hopefully we will see a change in direction in addition to that change in speed. So way over here, I would suggest that they're traveling about that direction. And over here, it's not huge, but there's a slight difference. Not a monstrous difference. There's a slight difference.
Oh, it's tricky.
There's always some point in this demonstration where I'm trying to convince myself that I'm seeing these things. Okay. Next. Okay. The funny little metal things with the red balls on the end, wherever they went to.
Yeah, floor.
Oh, on the floor. Of course they're. There. Are themselves wave generators. Pretty circular waves.
You can see the reflection through the lens.
So these circular waves, after they hit this straight barrier, come out more or less circular, but a lot bigger than they were. Almost as if they're coming from somewhere over here. Which is a thing you should remember from grade 10 optics. Images in plane mirrors or flat mirrors are on the other side of the mirror, roughly the same distance away from the mirror as the object is. So these waves are coming from a virtual source over here. And need Liam again. What we're going to try and do is position this so that that focal point of the parabola is exactly where these waves are being generated, which is close to there. So when I turn this thing on and these circular waves come out of this red ball and hit this parabolic barrier, what should they do when they reflect?
Circular standing wave?
Nope.
Like line, straight.
They'll come out straight because that focal point was produced when the waves were straight and hit the barrier and got focused. This is the reverse. They're now coming out of that focal point towards the barrier. They should reflect straight. We'll see. Kinda.
Close.
And then we're just guessing where that focal point is. But those are reasonably straight.
Wow.
That was better than the other class. Okay. The final thing.
Oh my god.
So, there's two different ways to look at this. One is to try and follow the bright lines along the floor. The other is to kind of defocus and just look at the floor, right? And if you do that, you can see the nodal lines very clearly. Can you see the nodal lines very clearly? The fuzzy gray patches in between the bright and dark lines. So, for example, there's one right about there, and there's another one right about there, and I'd say though, trying to figure out where the perpendicular bisector is. It looks like this is right on the perpendicular bisector.
Yeah.
Yeah, there's a bit of a phase issue between these sources. they're pretty close. This little knob here changes the phase relationship. You can make them go out of phase, but they're in phase and I'm happy with it, so I don't want to muck with it. But anyway, what I'm going to do now is increase the frequency of the generator, which will decrease the wavelength. Think of the last equation we looked at, which was for Young's double slit, but we can still use it here. Lambda equals delta x d over L. Okay? If I make the wavelength smaller, lambda on the left side of that equation, and don't change d, and I don't change L, whatever that is in this picture, delta x should also get smaller, which means that these nodal lines should move closer together. And they definitely have. And there's more of them, right? So I have to turn this off to explain that one. Think of the equation sine theta n equals n minus a half lambda over d. The left side of that, sine theta n, has a maximum value of 1. And if on the right-hand side the wavelength goes down, that means that the maximum possible value of n can now be higher and still have all of that stuff, n minus a half lambda over d, be less than 1. So I decrease the wavelength, n can get bigger, and there are more nodal lines existing. And if I do the opposite, I increase the wavelength, there are now fewer nodal lines. Some of them are disappearing off to the side. Now there's only 6. Now there's only 4. And I was way off on the perpendicular bisector. There's the perpendicular bisector. Somehow. That's a perspective issue. Oh, this thing's been rotated. That's the issue. It's hot too. Don't burn your finger. There we go. Okay.
Burned it. It hurt a lot.
So, right this very moment, or more or less, Nathan is working on his programming project and is doing a pretty good job of it to animate exactly this. He's got his circles going out, he's got the nodal points perfectly lined up, and he's got the nodal lines drawn, and he's got a little slider, or several sliders that allow me to change the frequency and the wavelength and the distance between the sources and the speed. Thank you. Okay, so I'm going to change one of those things here. Keep the wavelength as it is, right about there. I'm going to put the sources closer together. Okay, so again, look at the equation sine theta n equals n minus a half lambda over d. If d gets smaller, the denominator gets smaller, then that reduces the maximum possible value of n and still allows all of that to be less than 1, because sine theta n has to be less than 1. So I put those things closer together, there will be fewer nodal lines. There are fewer nodal lines. And if I put them as far apart as I can possibly manage, then I'm going to have to do a little balancing act here. There's a lot more nodal lines.
Fall asleep.
That thing on the ground feels like
Just
it's
like
moving
keep
out.
looking
Like,
at them
it
and watching
pitches
them as they move out.
Look, it's on the ceiling too.
Now, the point that I was illustrating there, right at the end, is when the frequency gets very large, and quite possibly this thing was behaving erratically when that happened, it gets very hard to see that interference pattern. Because if there is anything, it's kind of shifting around at a very high frequency. And the waves themselves, the water, probably can't even respond fast enough to create sensible waves. So that's kind of analogous to the difficulty in seeing the two-point interference from light waves, because the frequency is so very, very large and the wavelength is so very, very small. You have to have, some precision to get the light to show that interference pattern. I'm going to crank it back down a little bit here and just give you another 30 seconds or so of just staring at the nice, pretty lights on the floor. Oops. Nice and calm. That's nice. A little bit more. There we go.
What you could see.
Yeah, I know if I could get that, actually that, if I could get that projected on my ceiling, I might be able to fall asleep faster. Or not at all, I might just be staring at it all night.
Be scary though if you like woke up and you just have like 2 eyes. It's like, oh.
2 3 points next.
Okay, that's interesting. That's very interesting. The video just suddenly jumped from 8 minutes to 20. I don't know what happened there. Well, anyway.